Okay, in this video we're going to do an introduction to what are called nucleophiles and electrophiles. All right, these are really important when you're talking about reactions in organic chemistry. So first of all, back when we were talking about resonance structures, we showed that you can use these little curly arrows to show that how the electrons would move around within a molecule, but the electrons can also show how bonds are made or bonds are broken. All right, and that's going to be something that we're going to be doing a lot of when talking about these. All right, so first of all, a nucleophile. A nucleophile is a molecule, or it could actually be a single atom. But what has to be true is that there has to be an electron-rich atom that contains a lone pair, and that it's capable of forming a new bond to a new atom using that electron pair. All right, and the atom that nucleophiles are going to form that bond with are what are considered electrophiles. All right, so electrophiles are molecules that contain electron-poor atoms that are capable of accepting an electron pair from a nucleophile. All right, so we're going to talk about some specific examples in just a little bit, but we could also talk about these excuse me, generically. All right, so a common way to show a nucleophile, or just to represent it, is just to say Nu with the minus, with a negative charge. All right, and what that negative charge is going to represent is well, first of all, it could be negatively charged, but it also could be neutral. All right, the negative charge is going to represent an electron pair. All right, so an alternative way of doing this would be to show it like this, where you're showing nucleophile as if it were neutral, but showing an electron pair, or to show that negative charge, but to also show an electron pair. All right, so these would all three be acceptable ways to generically represent a nucleophile. All right, electrophiles are generally represented as a capital E with a positive charge. All right, and that positive charge is to indicate that there's an atom that has at least a slightly positive charge that's going to be attracted to the electron pair, attracted by the electron pair of that nucleophile. All right, and so whenever that lone pair on the nucleophile makes a bond with the electrophile, we say that it's attacking the electrophilic atom. All right, so we would say that the lone pair on this nucleophile attacks this electrophile right here, and when that happens, a new bond is going to get created. All right, so I just want to start by showing some common reactions where you would have a nucleophile and an electrophile. All right, so again, a nucleophile by definition is an electron-rich atom that's got an electron pair capable of making a bond. All right, and a good example of that is an alkoxide. All right, so all an alkoxide is an alcohol that's had an H plus removed. All right, so if you think about an alcohol that would have a single bond to a hydrogen, and if you plucked off that H plus and put the electrons back on the oxygen, you'd now have 3 lone pairs on that oxygen, and that gives it a negative charge. All right, so that thing right there is called an alkoxide, and that makes a pretty good nucleophile. All right, a good electrophile are what are called alkyl halides, or another way you can say these are halogenoalkanes. All right, so what makes this guy right here electrophilic is that this bond right here between the carbon and the bromine. All right, bromine is more electronegative than carbon, so that's going to pull these electrons a little bit towards the bromine. All right, another thing that makes it electronegative is that bromine this bond is capable of getting broken and the electrons going with the bromine. All right, so when this is generic right here, but this is a specific example. What this shows is that the nucleophile, specifically the electron pair on that oxygen, that's what makes it a nucleophile, attacks this carbon, and these electrons go onto the bromine. All right, and that makes this molecule right here. So this is it's drawn as a line angle structure, but this new carbon right here comes from this guy right here. That's a methyl group. All right, and the other product that you would have is bromide. All right, so right here, when it's in the molecule, it's got 3 lone pairs around that bromine, And when these electrons go onto the bromine to make bromide, this would have 4 lone pairs around it. All right. So another example is actually something that we learned about in the acid-base unit, which is the very simple reaction between a compound with a Lewis acid. All right, and remember, a Lewis acid was any compound that was capable of accepting a lone pair. All right, and the very famous Lewis acids tend to be either boron or aluminum things that have 3 bonds to them. All right, and the reason that those are Lewis acids is that when this thing right here is neutral, it's not obeying the octet rule. Remember, the octet rule would say that it would want to have 8 electrons around it because it's of its closest noble gas. And this guy right here only has 3 electron pairs around it. So it's capable of accepting another lone pair. So this molecule right here, this is an amine. All right, and amines, as opposed to alkoxide, amines are nucleophilic even when they're neutral. All right. So when this lone pair attacks that boron, it's going to make this species right here. And hopefully this right here looks familiar. It's the very classic Lewis-based Lewis acid reaction. All right. So an obvious question is, why isn't an alcohol all by itself that electrophilic? It's because oxygen is more electronegative than nitrogen, and so oxygen tends to hold on to those electron pairs a little bit more than nitrogen. Nitrogen is a little bit more willing to it's not quite as stingy with this electron pair, and so that makes that electron pair a little bit more willing to act as a nucleophile. Okay, so a third type of common nucleophile is this type of molecule right here, which is what's called an enolate. All right. The IB curriculum doesn't stress this type of nucleophile that much, but it's a very common one in organic chemistry. All right. So whenever the place that you're going to have an enolate is whenever you have hydrogens which are on a carbon right next to a carbonyl group. All right. And this carbon is what's called an alpha carbon. All right. If it was bonded to a carbon right here, the next carbon would be the beta carbon. All right. So hydrogens that are connected to alpha carbons, all right, which means hydrogens which are connected to carbons which are right next door to a carbonyl, all right, tend to be relatively acidic, which means that it's relatively easy for a base to pluck off an H plus, which now leaves this lone pair right here. All right, so this that lone pair can act as a nucleophile, and that can attack an electrophile. All right, and a very common electrophile that it could attack would be something like an aldehyde or another ketone. All right, and so the reason that aldehydes act as electrophiles is in this carbonyl group, all right, in this carbon-oxygen bond, the oxygen likes to pull the electrons more towards it because it's more electronegative. All right. And that makes this carbon here slightly positive. All right. So, excuse me, when you combine this enolate with an aldehyde, the enolate tends to act as a nucleophile, attacking this carbon. And when that happens, these electrons, one of the electron pairs in this bond, goes on to the oxygen. All right. And the thing that gets made there is this guy right here. All right. So this right here, this is the bond that's just gotten formed. All right, the 2 electrons that are in this single bond are the 2 electrons that were in the lone pair right here on this carbon. All right, and when these electrons went up to this oxygen, well, you used to have a double bond right here. Now you only have a single bond because the other bond is now the lone pair that's now up on this oxygen. And that's why we represent that with a negative charge right there. All right, and all this thing needs is to have some source of H plus, and when we could actually draw that, we could draw an arrow going from this negative charge to that H plus, and that would give you this molecule right here. All right. So again, the IB doesn't stress this type of reaction that much, but if you were to ever go on and take organic chemistry in college, this is a fairly common type of nucleophile and electrophile. All right, so before moving on, just a little bit about why do we call these things nucleophiles and electrophile? All right, well, the reason that this thing is called a nucleophile is because, if you think about the literal, translation of that, a nucleus lover. All right, so this carbon right here, if it's having if it has electrons pulled away from it, all right, that makes that carbon right there, the center of that carbon, more positive. There's a slight delta positive charge, and so it's called a nucleophile because you can think of it as an attraction for the nucleus of that atom right there. All right. Electrophile, it's the reason that it's an electrophile is that literally it would be lover of electrons. All right. It likes to have to accept electron pairs from things that are willing to donate electron pairs. So, some common examples of nucleophiles, all right? The first two are very similar to each other, either hydroxide or an alkoxide, all right? And the only difference is that for hydroxide, it's HO, and for an alkoxide, this would be an R group. It could be a methyl group, ethyl group, anything like that, all right? And the thing is, the thing I want to note here is that water isn't that great as a nucleophile. All right, water's not that nucleophilic, and the reason for that is if this right here, if this electron pair were to make a bond with an H+, all right, this would be just plain old water, and you would just have 2 electron pairs on that. Well, the thing with water is that since the oxygen is fairly nucleophilic, the oxygen is a little bit stingy with those electrons. It tends to want to hold on to them a little bit more and not make them that available for attacking electrophiles. All right, but if you again if this is water, picture there being a single bond to a hydrogen. If you take away an H+ and you make hydroxide, there's now a 3rd electron pair there. All right, and a hydroxide is a little bit more willing. The electron pairs on that hydroxide are a little bit more inclined to want to make bonds with electrophiles than if it was just plain old neutral water. All right. The same thing could be said about the relationship between an alkoxide and an alcohol. All right. So all an alkoxide is an alcohol that's had its H+ removed. All right. So as the alcohol, it's not that nucleophilic. It's happy to just to not interact with other things. But once you remove that H+, it wants to attack and make bonds with electrophiles. All right. Another example is an amine. All right. Notice here, whereas the hydroxide and the alkoxide had to be negatively charged in order to be nucleophiles, an amine is perfectly happy to be an electrophile even when it's neutral. All right. So the best example of an amine is NH3, which is ammonia. But notice that the 3 things coming off this nitrogen could either be R groups or they could be hydrogens, all right, or combinations of those, all right. So, so the amine is nucleophilic when it's neutral because the nitrogen is not quite as electrophilic as the oxygen, and so it tends not to pull the electrons quite as closely to it as an oxygen would, and that makes it a little bit more inclined to want to make bonds with other molecules, all right. Last example we'll talk about right now is this guy right here. This guy is cyanide, and even though like a lot of times cyanide sounds scary, as long as if you were working with it, you took relatively common sense precautions, which means don't let this thing right here see acid. All right, if this sees an acid like hydrochloric acid, that's when it gets dangerous because it emits a poisonous gas. But as long as it's in a basic solution, it's relatively safe as long as you don't want to touch it or drink it. But it's actually very useful as a chemical in organic reactions, right? So it's nucleophilic because when cyanide, you've got this lone pair right here, and that lone pair right there tends to be very nucleophilic. All right, and again, cyanide. It allows you to do some useful things because it's a very convenient way to just add another carbon to a molecule. All right, we'll talk about common electrophiles in the next video.